In the 21st century, China has emerged as a new leader in lunar exploration. Through its Chang'e missions, the nation has uncovered new details about the moon's geology and history by landing on the far side and returning lunar samples. These modern achievements are part of a long story of discovery, a chain of breakthroughs stretching from the earliest observers to today's cutting-edge missions. China's recent lunar missions have provided groundbreaking scientific data. Samples returned by Chang'e 5 in 2020 allowed scientists to precisely date volcanic activity on the moon, which helped refine models of solar system history. This material also confirmed the presence of water in the form of ice and hydrated minerals locked within the soil. Meanwhile, on the moon's previously unexplored far side, the Chang'e 4 lander provided data confirming the moon's layered internal structure of a crust, mantle, and a small, partially molten core. The mission is also studying seismic activity, or moonquakes, in this region. Additionally, China's rovers have studied the unique properties of lunar dust, regolith, the effects of micrometeorite impacts, and traces of ancient magnetism in lunar rocks. But to truly understand what China has found on the moon, we must retrace this chain of discoveries that revealed the moon's secrets, one by one. Discovery 1. The first telescopic glimpse of the moon. In 1609, Galileo Galilei pointed his primitive telescope toward the moon and made one of the most revolutionary discoveries in the history of science. Until that moment, most people believed the moon was a flawless divine sphere, a perfect creation hanging in the heavens. Philosophers like Aristotle had long argued that celestial bodies were smooth and unchanging, unlike the imperfect Earth below. But Galileo's telescope shattered this ancient worldview. Through his lens, he saw jagged mountains, deep valleys, and shadowed craters carved into the lunar surface. These features revealed that the moon was a world of rock and dust, not some mystical glowing orb. Galileo sketched what he saw, publishing drawings that shocked Europe. His discovery challenged the prevailing religious and philosophical beliefs of the time, igniting controversy, but also inspiring future generations of scientists. For the first time in human history, the moon was not just a light in the night sky. It was a real, physical world waiting to be explored. Discovery 2. Early lunar mapping. Following Galileo's breakthrough, astronomers across Europe began turning their telescopes to the moon, seeking to map its unfamiliar terrain. In the 17th century, English astronomer Thomas Harriot and Polish astronomer Johannes Hevelius drew some of the earliest sketches of lunar landscapes, but their maps lacked accuracy. By the 18th century, improvements in telescopes led to more precise observations, and astronomers began naming craters, seas, maria, and mountains, often after famous scientists and philosophers. The true leap came in the 1830s, when Wilhelm Beer and Johann Heinrich Madler in Germany published the first reliable lunar atlas, Mappa Selenographica. Their maps revealed the moon in far greater detail than ever before, marking the beginning of modern selenography, the study of the moon's surface. These maps became invaluable for both scientific study and, eventually, planning spacecraft trajectories centuries later. What began as crude drawings had evolved into scientific cartography, proving that humanity's connection to the moon was shifting from poetic imagination to scientific precision. Discovery 3. The moon's lack of atmosphere. For centuries, people imagined that the moon might be inhabited. Without the ability to test, writers and dreamers speculated about forests, rivers, and even lunar civilizations hidden beyond our sight. But in the 19th century, spectroscopy finally gave scientists the tools to answer the question. By analyzing the light reflected from the moon, researchers discovered the absence of atmospheric absorption lines that Earth's sky produces. This meant the moon had no breathable air, no clouds, and no weather. Its surface was exposed directly to the vacuum of space. This finding was devastating for romantics who imagined lush lunar landscapes, but it was vital for science. It explained why the moon's craters and features remained so perfectly preserved for billions of years. There was no wind, rain, or erosion to alter them. It also meant astronauts would need to bring their own life support systems if they ever hoped to visit. The discovery cemented the moon's status as a barren, airless body. Discovery 4. Understanding lunar craters. When early astronomers looked at the moon's cratered surface, they debated their origin. Many assumed they were volcanoes, since Earth's craters were often volcanic. For centuries, this explanation dominated scientific thought. But in the late 19th century, geologists like Grove Carl Gilbert began suggesting a radical alternative. The moon's craters were created by impacts from asteroids and comets. Though controversial at the time, this theory eventually gained traction as scientists studied crater shapes and ejecta patterns that didn't match volcanic activity. The idea of impact cratering would later prove essential not only for understanding the moon, but for planetary science in general. It explained how celestial bodies across the solar system, from Mercury to Mars, bore similar scars. This realization reframed the moon as a witness to the violent early history of the solar system. Each crater was not just a hole in the ground, but a cosmic record of collisions dating back billions of years. Discovery 5. The moon's influence on Earth. Long before humans understood the mechanics of gravity, they noticed the tides rising and falling in rhythm with the moon. By the 18th and 19th centuries, physicists like Isaac Newton and later Pierre-Simon Laplace mathematically described how the moon's gravitational pull drives Earth's tides. But the influence of the moon goes beyond the oceans. Studies in the 19th century showed that the moon's gravitational interaction also stabilizes Earth's axial tilt, preventing wild climate swings that might make life impossible. Without the moon's steadying presence, Earth could wobble chaotically over time, leading to catastrophic environmental changes. This discovery reframed the moon not only as a companion, but as a guardian of life on Earth. Its invisible gravitational hand helps maintain the stability of our planet's climate, a subtle but essential role that continues to this day. Far from being a passive satellite, the moon actively shapes the conditions that make Earth habitable. Discovery 6. The first photographs of the moon. In 1840, American scientist John William Draper made history by taking the first successful photograph of the moon using a daguerreotype. The image was blurry, but it captured something drawings never could: objective proof of lunar features. By 1865, advances in photography allowed Lewis Rutherford to produce far sharper lunar photos, revealing craters and Maria with clarity. Photography revolutionized lunar science by providing a permanent, shareable record that could be studied by scientists worldwide. Unlike sketches, which were subject to human interpretation, photographs offered a reliable dataset. This opened the door for more systematic mapping and scientific analysis. By the late 19th century, lunar photography became a cornerstone of astronomy, creating an archive of images that helped track changes in lighting, shadows, and even meteor impacts. These early photographs gave humanity its first real sense of the moon as a tangible world, preserving its appearance for future generations to study. Discovery 7. Spectral analysis and lunar composition. Spectroscopy in the late 19th century allowed astronomers to peer deeper into the moon's secrets. By spreading its reflected light into a spectrum, scientists could analyze the fingerprints of chemical elements. This technique revealed that the moon was made of silicate rocks, much like Earth's crust. Gone were the fanciful ideas of a metallic or glassy moon. Instead, it was confirmed to be a rocky body, forged in the same cosmic processes as Earth. This discovery bridged lunar science with geology, allowing researchers to compare terrestrial and lunar materials long before samples were brought back. Spectral analysis also confirmed the lack of atmospheric gases and helped estimate the composition of the Maria and Highlands. For the first time, scientists began to see the moon not as a mysterious alien body, but as a familiar relative of Earth, made from the same basic ingredients of the solar system. Discovery 8. The Far Side Mystery. The moon has always shown the same face to Earth, a phenomenon known as tidal locking. This was explained mathematically in the 19th century, but it created a profound mystery. What did the far side look like? Generations of astronomers speculated about hidden oceans, civilizations, or unknown landscapes on the unseen hemisphere. The far side remained one of astronomy's greatest enigmas, a reminder that even our closest neighbor had secrets. Artists and writers filled the gap with imagination, while scientists patiently awaited the day when technology could reveal the truth. It wasn't until 1959, with the Soviet Luna 3 mission, that humanity finally glimpsed the hidden face. But for centuries prior, the far side represented both the limitations of Earth-based observation and the allure of the unknown. This mystery fueled the drive for space exploration, proving that some answers could only be found by leaving Earth. Discovery 9. Radio echoes from the moon. In the early 20th century, engineers experimenting with radio technology discovered that signals could be bounced off the moon and received back on Earth. This was first achieved in 1946 by the U.S. Army's Project Diana, which successfully sent radar pulses to the moon and detected the echoes. The experiment confirmed the exact distance to the moon with unprecedented accuracy and proved that radio waves could cross the vast emptiness of space. This discovery had profound implications, not just for lunar science, but for communications and defense. It showed that the moon could serve as a giant passive reflector, enabling potential communication systems. It also laid the groundwork for using radar to map the lunar surface, giving scientists insight into its roughness, texture, and reflectivity. Project Diana marked the first intentional two-way communication between Earth and another world, even if it was just in the form of radar echoes. Discovery 10. Early theories of the moon's origin. By the late 19th and early 20th centuries, scientists were determined to explain how the moon came to be. Three main theories emerged. The capture theory suggested the moon formed elsewhere and was later trapped by Earth's gravity. The co-accretion theory argued that Earth and Moon formed side by side from the same disk of material around the young Sun. The fission theory proposed that the Moon was once part of Earth, ripped away when our planet spun much faster. Each theory had strengths and weaknesses, but none could fully explain all observations. The debate would continue for decades, fueled by new data from telescopes and later Apollo samples. These early hypotheses showed humanity's determination to understand cosmic origins, even without the evidence that would later come from space missions. Theories about the moon's birth reflected not only science, but the limits of imagination in an era before spaceflight. Discovery 11. The lunar eclipse and scientific measurements. For thousands of years, people witnessed the moon turn blood red during eclipses, sparking myths of omens and celestial battles. But by the 19th century, scientists realized that lunar eclipses provided valuable opportunities to study both Earth and the moon. When Earth passes between the Sun and the Moon, its atmosphere bends sunlight, casting a reddish glow onto the lunar surface. By analyzing that light, astronomers could deduce information about Earth's atmosphere, its composition, dust content, and even volcanic activity. Eclipses also allowed scientists to refine calculations of the Earth-Moon-Sun geometry, improving our understanding of orbital mechanics. Perhaps most importantly, eclipses demonstrated that celestial phenomena followed predictable, calculable laws, not mystical forces. Chinese astronomers, with their long history of eclipse records, contributed greatly to this understanding, showing how ancient observations could be married with modern physics. The lunar eclipse, once feared, became a scientific tool, a window into both our planet and its companion. Discovery 12. Measuring the moon's distance with precision. Humans have long known that the moon's distance changes slightly as it orbits Earth. But accurate measurements were difficult until the modern era. In the 19th century, astronomers used triangulation and parallax methods, comparing the moon's position in the sky from different points on Earth to estimate its distance. Results improved dramatically with the development of radar in the 20th century. Project Diana in 1946, mentioned earlier, bounced radio signals off the moon, providing distance measurements accurate to within a few hundred meters. Later, laser reflectors placed on the moon during the Apollo missions and by Chinese Chang'e landers enabled measurements accurate to within centimeters. These findings revealed that the moon is slowly drifting away from Earth at about 3.8 centimeters per year. This seemingly small discovery reshaped our understanding of celestial mechanics and the evolution of the Earth-Moon system. It confirmed that tidal interactions between the two bodies are ongoing, shaping their future relationship. Discovery 13. The moon's librations. While the moon always shows the same face due to tidal locking, careful observation in the 19th century revealed that it actually wobbles slightly. This phenomenon, called libration, allows observers on Earth to see about 59% of the lunar surface over time, instead of just 50%. Librations occur because the Moon's orbit is slightly elliptical and tilted relative to Earth's equator. These subtle shifts gave astronomers tantalizing glimpses of regions near the lunar limbs, areas that would otherwise remain hidden. Early selenographers used librations to improve their lunar maps, expanding humanity's knowledge of the visible Moon. Later, this understanding became essential for planning spacecraft missions and choosing landing sites, as it allowed scientists to anticipate the visibility of certain features. For China's space program, knowledge of libration would prove useful centuries later when selecting sites for Chang'e landers and rovers. What seemed like a minor wobble was actually a gateway to new discoveries. Discovery 14: Polar regions and the mystery of shadows. Throughout the 19th century, astronomers speculated about the Moon's poles, which were difficult to observe due to their extreme angles. Some theorized that deep craters near the poles could harbor eternal darkness, shielding them from sunlight. This idea fascinated scientists because permanently shadowed regions might preserve ancient material unchanged for billions of years. These cold traps became a focus of scientific imagination, suggesting that the lunar poles could be natural time capsules of the solar system. While Earth-based telescopes could not confirm this, the hypothesis persisted into the 20th century, setting the stage for modern missions. Today, China's Chang'e 4 and other spacecraft have made polar exploration a priority, confirming that these regions indeed hold water ice. But the idea began much earlier, as a scientific mystery born of shadows and geometry. Even without modern technology, 19th century scientists understood that the poles might hold secrets unlike any other part of the Moon. Discovery 15: The lunar highlands and Maria. By the mid-1800s, astronomers noticed two distinct types of lunar terrain: the bright, rugged highlands and the darker, smoother plains called Maria. Early observers assumed the Maria were seas, hence the name derived from the Latin word for seas. But as telescopes improved, it became clear that these regions were not water-filled, but solidified lava flows. This realization hinted at a volcanic past for the Moon. Scientists began classifying surface features, identifying mountain ranges, rills, valleys, and domes. The contrast between the highlands and Maria raised fundamental questions about the Moon's geological history. Why were some regions ancient and cratered, while others were relatively smooth? These questions pushed lunar science toward geology, long before space probes could confirm volcanic activity. Today, we know the Maria formed billions of years ago, when giant impacts triggered lava to flood low-lying basins. The division between highlands and Maria tells the story of a once dynamic Moon. Discovery 16: The great debate on volcanism versus impacts. One of the most heated debates in 19th century lunar science was whether craters were volcanic or impact in origin. Many scientists, influenced by terrestrial geology, insisted that volcanoes must have created the Moon's pitted surface. After all, Earth's craters were mostly volcanic. But a growing minority argued for impacts, pointing to the circular shapes and ejecta patterns. This debate raged for decades, with neither side able to definitively prove its case. It was not until the mid-20th century, with spacecraft data, that the impact hypothesis triumphed. Still, the debate itself was important. It forced scientists to carefully study crater morphology, compare lunar features with Earth's geology, and develop new theories about planetary processes. For China's later lunar missions, this historical debate underscored the importance of gathering samples to settle geological questions. What began as disagreement ultimately advanced the science of planetary geology and laid the foundation for modern lunar exploration. Discovery 17. The Moon's role in timekeeping. Throughout human history, the Moon has shaped calendars and timekeeping. In the 19th century, astronomers refined the use of lunar observations for navigation and clock regulation. By tracking the Moon's position relative to stars, sailors could determine longitude at sea, making lunar measurements a practical tool for exploration. The Moon's predictable phases also influenced the design of early mechanical calendars. More importantly, precise lunar observations revealed subtle irregularities in its orbit, which could only be explained by Newton's theory of gravitation. These observations confirmed that the Moon was not just a passive companion, but an active participant in celestial mechanics, influenced by Earth, the Sun, and even other planets. China, with its ancient tradition of lunar calendars, contributed a cultural dimension to this scientific role. The Moon's cycles guided agriculture, festivals, and rituals, bridging the gap between scientific measurement and human life. Thus, the Moon became both a cosmic clock and a cultural symbol. Discovery 18. Early lunar photography in detail. While John Draper captured the first blurry image of the Moon in 1840, the art of lunar photography blossomed in the latter half of the 19th century. Astronomers like Warren de la Rue in England and Lewis Rutherford in America developed techniques to capture the Moon in remarkable detail. De la Rue even constructed a photoheliograph, a special telescope designed for photographing celestial bodies, which he used to produce lunar stereographs, 3D images that gave the Moon a sense of depth. These photographs were not just scientific tools, but cultural marvels, displayed in exhibitions and journals. They allowed ordinary people to see the Moon's craters and mountains for the first time, bringing astronomy into the public imagination. For scientists, they provided an objective record that could be measured, compared, and analyzed. Lunar photography represented a union of science, art, and technology, capturing the Moon in ways that sketches never could. Discovery 19. Chinese astronomical contributions revived. While much of 19th century lunar science was driven by Europe, China's ancient traditions of astronomy were rediscovered and appreciated by modern scholars. Records from the Han and Tang dynasties documented eclipses, comets, and lunar phenomena with extraordinary precision. Western scientists began studying these records, realizing that they provided data stretching back thousands of years, far earlier than European records. These ancient Chinese observations became invaluable for confirming long-term changes in the Moon's orbit and Earth's rotation. The 19th century revival of Chinese astronomy also influenced China's future role in space exploration, as scholars sought to connect their heritage with modern science. In many ways, China's 21st century lunar program is an extension of this rediscovery, blending ancient tradition with cutting-edge technology. The Moon, long celebrated in Chinese poetry and philosophy, once again became a bridge between culture and science, showing that discovery is not only about new data, but also about reconnecting with history. Discovery 20. The Moon and the Birth of Science Fiction. While not a scientific discovery in the strict sense, the 19th century also saw the Moon inspire a new genre, science fiction. Writers like Jules Verne, with From the Earth to the Moon, 1865, and later H.G. Wells with The First Men in the Moon, 1901, imagined journeys to our celestial neighbor using the technology and ideas of their time. These works influenced public perception of the Moon, blending scientific possibility with imaginative storytelling. They speculated about lunar landscapes, civilizations, and technologies long before rockets existed. In turn, these stories inspired generations of scientists and engineers who eventually made space travel a reality. China, too, embraced lunar symbolism in literature, poetry, and mythology, blending cultural imagination with scientific ambition. Science fiction thus became part of the Moon's legacy, showing that discovery is not limited to telescopes and equations, but also thrives in human creativity. Discovery 21. The Moon's geological layers. By the late 19th century, geologists began speculating about what lay beneath the Moon's surface. Telescopes revealed mountains, plains, and craters. But what was the Moon made of internally? Some scientists suggested it might have a metallic core like Earth, while others believed it was a cold, solidified rock with no molten center. Early spectral analysis hinted at silicate-rich material on the surface, leading to theories that the Moon was geologically dead. Yet debates persisted about whether volcanic processes shaped its features or if impacts dominated. This curiosity about the Moon's inner layers marked the beginning of lunar geology, even without physical samples. Later, seismometers left by Apollo astronauts, and more recently, data from China's Chang'e 4 mission, confirmed that the Moon indeed has a layered structure: crust, mantle, and a small, partially molten core. What 19th century scientists imagined through reason and theory would only be confirmed centuries later through exploration. Discovery 22. The idea of water on the Moon. For centuries, people speculated about lunar seas. When telescopes proved that the Maria were solid basalt, the dream of oceans vanished. But by the late 19th century, some astronomers theorized that water might still exist, hidden in polar shadows or locked in the soil. This idea was ridiculed for years, as the Moon's lack of atmosphere made liquid water impossible. Yet the speculation never died. Modern missions, including India's Chandrayaan-1 and China's Chang'e 5, have confirmed that the Moon indeed holds water in the form of ice and hydrated minerals. Permanently shadowed craters at the poles act as deep freezers, storing ice that may one day support lunar colonies. The fact that 19th century astronomers even considered this possibility shows their forward thinking. Today, China prioritizes polar exploration precisely because of these early hypotheses, demonstrating how even speculative science can spark future exploration. Discovery 23. The Moon's gravitational influence on Earth's rotation. In the 19th century, scientists discovered that the Moon doesn't just cause tides. It also gradually slows Earth's rotation. This phenomenon, known as tidal braking, transfers rotational energy from Earth to the Moon, causing our days to slowly lengthen while pushing the Moon farther away. At first, the idea that the Moon was subtly altering the pace of time itself seemed extraordinary. Yet geological evidence supported it. Ancient coral fossils revealed growth rings that implied shorter days hundreds of millions of years ago. The Moon was acting as a cosmic regulator, not only shaping tides but influencing the very rhythm of life. Today, laser reflectors confirm the Moon's recession from Earth. China's lunar program relies on this understanding to model orbital mechanics for long-term missions. The discovery demonstrated that the Earth-Moon system is not static but dynamic, locked in an ancient gravitational dance that continues to evolve. Discovery 24. The concept of lunar soil, regolith. By the late 19th century, astronomers studying the play of light on the lunar surface realized that the Moon was covered in a layer of dust. They noticed that shadows appeared softer than expected and theorized that fine particles coated the rocks. This was the first hint of what we now call regolith, the blanket of fragmented rock and dust created by billions of years of meteorite impacts. The idea was controversial. Some thought the surface was hard bedrock. The true answer came in the 20th century, when robotic landers confirmed the powdery soil. Later, Apollo astronauts described their boots sinking into several centimeters of dust, and China's Chang'e rovers sent back images confirming regolith of varying thickness across different regions. The 19th century suspicion of lunar soil turned out to be correct, laying the foundation for modern lunar geology and raising practical concerns for future explorers about dust management. Discovery 25. The Moon's role in evolutionary theories. The 19th century was a revolutionary time for biology, thanks to Charles Darwin's On the Origin of Species, 1859. Scientists began connecting astronomy with life sciences, speculating that the Moon's gravitational pull, responsible for tides, may have influenced the development of early life on Earth. Some argued that tidal pools created by the Moon's influence provided ideal environments for primitive organisms to evolve. This theory suggested that without the Moon, life on Earth might have unfolded differently, or perhaps not at all. Although impossible to prove definitively, the idea showed how interconnected celestial mechanics and biology could be. Today, astrobiologists extend this reasoning to exoplanets, asking whether moons might stabilize climates or foster life elsewhere. The Moon thus became not only an astronomical object, but a potential key to understanding life's origins. China's lunar exploration ties into this narrative by studying how cosmic processes influence planetary habitability. Discovery 26. The Moon and geological time. By studying the Moon's craters and landscapes in the 19th century, geologists realized that celestial bodies could preserve a record of cosmic history. Unlike Earth, where weather and tectonics erase ancient scars, the Moon retained billions of years of impact records. Scientists began to think of the Moon as a time capsule of the early solar system. This concept laid the groundwork for using lunar geology to understand planetary evolution. When China's Chang'e 5 mission returned lunar samples in 2020, scientists used them to date volcanic activity on the Moon, refining models of solar system history. This modern breakthrough traces back to the 19th century realization that the moon's surface could reveal deep time. By linking geology with astronomy, researchers established the moon as a cosmic archive, preserving events long lost on Earth. The moon, once a symbol of mystery, became a scientific historian. Discovery 27. Double star observations and lunar occultations. In the 19th century, astronomers discovered that when the moon passes in front of stars, the timing of these occultations could be used to measure stellar positions with great precision. By carefully recording the moment a star disappeared and reappeared behind the moon, they refined star catalogs and even discovered new binary systems. Lunar occultations became an essential tool for astrometry, the science of measuring celestial positions. These observations also confirmed details of the moon's orbit and shape. The practice demonstrated how the moon, though not a light source itself, could act as a tool for studying the universe beyond. This was one of the first examples of using the moon as a scientific instrument, a concept that echoes today as astronomers consider building radio telescopes on the moon's far side, shielded from Earth's noise. China has expressed interest in such projects, continuing this legacy of lunar-assisted discovery. Discovery 28. The moon and cultural astronomy. While scientific discoveries accelerated in the 19th century, the moon's cultural importance remained equally profound. Chinese traditions, such as the Mid-Autumn Festival, celebrated the moon as a symbol of reunion and reflection. Scholars in the Qing dynasty combined classical poetry with emerging Western astronomical ideas, merging culture and science. The moon became a bridge between heritage and progress. Western societies, too, romanticized the moon in art and music, blending observation with imagination. This cultural fascination was not mere decoration. It drove public support for astronomy and exploration. People were captivated by telescopic drawings and photographs because the moon already lived deeply in their cultural consciousness. For China, blending ancient reverence with modern exploration has become a recurring theme. The moon's role in cultural astronomy demonstrates that science does not exist in isolation. It thrives when it resonates with human meaning and tradition. Discovery 29. Lunar parallax and Earth's size. In the 19th century, astronomers used the moon to refine measurements of Earth's size and shape. By observing the moon simultaneously from distant locations, they calculated its parallax, the apparent shift in position relative to background stars. These measurements provided crucial data for determining Earth's radius with greater accuracy. The technique also improved lunar orbital models, helping predict eclipses and occultations with precision. For China, where ancient astronomers had long sought to understand the cosmos through careful sky watching, these modern refinements echoed their traditions of precision. Lunar parallax demonstrated how our nearest neighbor could act as a cosmic yardstick, linking Earth to the heavens. Today, parallax remains a foundational concept in astronomy, used to measure distances to stars. The moon was humanity's first testing ground for this method, proving once again that discovery often begins close to home. Discovery 30. Early concepts of lunar exploration. By the late 19th century, dreamers began sketching ideas for machines that could travel to the moon. Though rockets were not yet practical, visionaries like Konstantin Tsiolkovsky in Russia and Wan Hu in Chinese legend, symbolically, represented humanity's ambition to reach beyond Earth. Tsiolkovsky's writings described space travel using multi-stage rockets, oxygen supplies, and orbital mechanics, all essential concepts later realized in the 20th century. At the same time, popular culture embraced stories of lunar voyages, from Jules Verne to speculative newspapers. These early concepts may have been fanciful, but they planted the seeds of real engineering. For China, which centuries earlier imagined celestial journeys in folklore, these 19th century visions aligned with cultural imagination. Today, the Chang'e program, named after the moon goddess, fulfills both the scientific and symbolic dreams of those early thinkers. What began as speculative sketches became the blueprint for humanity's actual path to the moon. Discovery 31. The moon's albedo and reflectivity. In the 19th century, scientists began carefully measuring how much sunlight the moon reflects. This property, known as albedo, was surprisingly low, meaning the moon was far darker than most people imagined. To the naked eye, the moon appears bright in the night sky, but compared to Earth's clouds or snowy landscapes, it reflects much less light. Early studies estimated the albedo at around 7 to 12%, confirming that the lunar surface was covered in dark basaltic rock and dust, rather than shiny material. This finding corrected misconceptions about the moon being made of silver or other reflective metals. Understanding albedo was important for energy balance calculations, and later for planning spacecraft landings, since it affected how hot the surface could get under sunlight. Modern Chinese missions like Chang'e 4 and Chang'e 5 have refined albedo measurements with high-precision instruments, but the groundwork was laid in the 19th century, when scientists first recognized the moon as a surprisingly dark world. Discovery 32. The moon's lack of magnetism. Magnetism was another puzzle for 19th century scientists. On Earth, a magnetic compass always points north due to the planet's strong magnetic field. But when experiments were conducted with sensitive instruments aimed at the moon, they showed no sign of a global lunar magnetic field. This suggested that the moon lacked the molten, convecting core responsible for Earth's magnetism. While some believed the moon might have once had magnetic activity, by the late 1800s it was generally agreed that it was magnetically dead. This discovery was crucial because it explained why the moon was more vulnerable to solar radiation and cosmic impacts. Later, Apollo missions confirmed that while some lunar rocks retained remnant magnetism, evidence of an ancient magnetic field, the moon as a whole has no protective shield today. China's recent lunar missions continue investigating this mystery, searching for traces of past magnetism to better understand how the moon evolved internally. Discovery 33. The first lunar spectrographs. By the mid-19th century, the invention of the spectrograph allowed astronomers to analyze the moon's reflected light in unprecedented detail. Joseph von Fraunhofer's discovery of absorption lines in sunlight had already revolutionized astronomy, and applying this method to the moon confirmed that its spectrum matched that of the sun. This meant the moon had no light of its own. It simply reflected sunlight. Spectrographs also revealed subtle differences in reflectivity across lunar regions, proving that the Maria and highlands were composed of different materials. This reinforced the idea that the moon had a complex geological history, not a uniform surface. Spectrography also became a tool to rule out fanciful ideas of lunar vegetation or oceans, since no atmospheric or organic signatures were detected. The moon was confirmed to be a barren, rocky satellite. These discoveries laid the foundation for later mineralogical studies, including those carried out by China's Chang'e 5 sample return mission. Discovery 34. The moon's thermal properties. Another surprising discovery in the late 19th century was the extreme variation in lunar surface temperatures. Using infrared measurements, scientists realized that the moon became blisteringly hot during the day and bitterly cold at night. Without an atmosphere to trap or distribute heat, temperatures swung from over 120 degrees in sunlight to below 170 degrees in darkness. This realization emphasized how hostile the lunar environment was for future explorers. The findings also reinforced the idea that the moon lacked an atmosphere or water, since either would have moderated these extremes. Today, this understanding guides engineering for lunar missions, including Chinese rovers that must survive 2-week-long nights by going into hibernation. The study of the moon's thermal properties not only revealed its alien environment, but also highlighted the challenges humanity would face in establishing a permanent presence there. It turned the moon from a romantic object into a harsh, unforgiving world. Discovery 35. The moon's orbital resonances. In the 19th century, mathematicians applied Newton's laws to study the moon's orbit in detail. They discovered subtle resonances, mathematical harmonies between the moon, Earth, and Sun. These resonances explained why the moon's orbit is stable over long timescales, even though gravitational pulls from the Sun and other planets constantly tug at it. They also clarified why the moon's orbit is tilted about 5 degrees relative to Earth's, which prevents eclipses from happening every month. These insights turned lunar motion from a mystery into a predictable system, showing that celestial mechanics could account for even the smallest irregularities. Chinese astronomers, who had long calculated eclipse cycles, found modern validation for their historical records in these mathematical discoveries. Today, orbital resonance studies are key to planning spacecraft trajectories, and China's Chang'e missions rely on the same physics to navigate to and from the moon with precision. Discovery 36. Early micrometeorite impact theories. During the 19th century, astronomers began to wonder whether tiny meteorites constantly bombarded the moon. Since Earth's atmosphere burns up most small meteors, they hypothesized that the moon, with no protective shield, must be littered with micro-impacts. This theory explained the fine dust layer some believed coated the lunar surface. Though unproven at the time, later missions confirmed that the regolith is indeed the product of countless micrometeorite strikes over billions of years. These impacts pulverized rock into powder and created a chemically unique soil full of glassy fragments. Modern Chinese missions like Chang'e 4 continue studying micrometeorite effects, especially how they interact with solar radiation to form new chemical compounds. What began as a 19th century speculation turned out to be central to lunar geology, proving that the moon's quiet appearance hides a history of relentless bombardment from space. Discovery 37. The moon's subtle shape. oblateness. Careful 19th century measurements revealed that the moon was not a perfect sphere but slightly elongated, with its longest axis pointing toward Earth. This discovery, made through telescopic observations and mathematical modeling, was an important step in understanding tidal locking. The moon's elongated shape explained why it always presented the same face to Earth. Its bulge was gravitationally captured over time. This finding not only clarified the moon's orbit, but also supported theories that it had once been more geologically active, with internal processes shaping its figure. Later spacecraft confirmed the moon's slight oblateness and mass concentrations, mascons, beneath large impact basins, which further distort its gravitational field. Today, China's Chang'e orbiters map these anomalies with incredible accuracy, but the first hints came from 19th century astronomers studying the moon's imperfect roundness. It was a subtle but profound discovery that reshaped our view of lunar dynamics. Discovery 38. The moon's connection to meteor showers. By the late 1800s, astronomers studying meteor showers such as the Perseids and Leonids began connecting them with cometary debris. They speculated that the moon, lacking an atmosphere, must also be bombarded by these same streams of particles. This realization tied the moon to the broader solar system environment, showing that it was constantly shaped by external forces. The hypothesis helped explain the countless craters seen on its surface. Unlike Earth, where meteor showers burn up as fleeting streaks in the sky, on the moon they leave permanent scars. Today, monitoring lunar flashes caused by meteoroid impacts remains an active area of research, with China's telescopes and orbiters contributing to the data. The 19th century idea that meteor showers were a shared phenomenon between Earth and Moon deepened our understanding of space as a connected system, not isolated worlds. Discovery 39. The Moon as a test for relativity. Toward the end of the 19th century, advances in physics suggested that Newton's laws might not explain everything. Precise lunar observations revealed tiny anomalies in its orbit, raising questions about whether gravity worked exactly as Newton described. These irregularities became part of the motivation for developing Einstein's theory of general relativity in the early 20th century. Though relativity wasn't formulated until 1915, the seeds were planted by lunar data collected in the 1800s. This showed that the moon was not just an object of curiosity, but a testing ground for the deepest laws of physics. Later, lunar laser ranging experiments, some still using retroreflectors placed by Apollo and Chang'e missions, proved general relativity correct with incredible precision. Thus, the moon helped bridge the gap between classical mechanics and modern physics, influencing some of the greatest breakthroughs in science. Discovery 40. The moon and the expansion of global astronomy. The 19th century was a time of international collaboration in science, and the moon played a central role. Observatories in Europe, America, and Asia all contributed to lunar mapping, photography, and theoretical studies. China, while experiencing political turmoil, still maintained astronomical traditions that were later integrated with Western science. The global fascination with the moon made it a universal object of study, transcending borders and cultures. Lunar atlases were published, photographs circulated in newspapers, and lectures captivated the public. This collective effort demonstrated that the moon was not the property of any one nation, but a shared frontier of knowledge. Today, China continues this tradition by collaborating with international partners on lunar exploration projects, from data sharing to joint missions. The moon's ability to unite humanity in the pursuit of discovery began in the 19th century, laying the foundation for the cooperative spirit of modern space science. Discovery 41. The moon and tidal science. In the 19th century, scientists deepened their understanding of how the moon influenced Earth's tides. While earlier civilizations had long observed the connection, precise measurements and mathematical modeling revealed just how powerful the lunar gravitational pull was. Oceanographers noticed that not only did the moon cause predictable high and low tides, but its alignment with the sun created dramatic spring and neap tides. This relationship showed that the moon had a measurable daily influence on life on Earth. Farmers timed planting seasons, sailors calculated navigation routes, and coastal communities learned to predict flooding risks more accurately. The discovery also highlighted the moon's role as a stabilizer of Earth's oceans and climate. Without it, Earth's tides would be weaker, ecosystems less dynamic, and human history potentially very different. Today, China uses satellite oceanography to study tidal effects with extreme precision, but the foundation of tidal science comes from these 19th century lunar insights. Discovery 42. The first lunar photography atlases. The invention of photography in the 19th century revolutionized lunar studies. For centuries, astronomers relied on drawings, which often varied depending on the observer's skill or artistic style. But in 1840, John William Draper captured one of the first daguerreotype images of the moon, changing astronomy forever. Soon, detailed photographic atlases were produced, showing craters, mountains, and Maria in striking accuracy. These images allowed astronomers across the world to study the moon without needing powerful telescopes of their own. By the late 1800s, photography revealed surface details invisible to the naked eye, confirming theories about volcanic origins, crater patterns, and even subtle surface textures. China later adopted these techniques when building its own modern lunar mapping programs. Today, Chinese missions like Chang'e 2 and Chang'e 4 carry high-resolution cameras, continuing a legacy that began with those first grainy black-and-white photos that stunned 19th century audiences. Discovery 43. The Moon and Geodesy. Geodesy, the science of Earth's shape and gravitational field, found an unlikely partner in the moon. In the 19th century, astronomers realized that by measuring the moon's distance and position with great precision, they could also refine measurements of Earth itself. Lunar occultations, eclipses, and transits became tools for charting the size of our planet and confirming the equatorial bulge caused by Earth's rotation. The moon, in this sense, was used almost like a cosmic benchmark against which Earth could be measured. These measurements advanced global cartography, helping navigators and scientists alike create more accurate world maps. The precision gained through lunar geodesy also laid early groundwork for what centuries later would become satellite navigation. Today, with the help of China's Chang'e orbiters, this field has reached new heights. High-resolution 3D maps of the Moon now serve as vital data sets not only for lunar exploration, but also for improving Earth's GPS systems. What began as attempts to understand our planet better through the Moon has become a shared science that connects Earth and space in one framework. Discovery 44. The Moon's role in ancient climate studies. For centuries, people observed that the Moon's cycles seemed to influence Earth's environment. In the 19th century, scientists began to seriously test this idea by connecting the Moon's orbital variations to long-term climate patterns. Building on ancient records, they explored how nodal cycles and precession might explain changes in rainfall, droughts, and even ice ages. These early investigations foreshadowed what we now call Milankovitch cycles, planetary-scale rhythms that link celestial mechanics with climate change. The Moon became a kind of climate clock, allowing researchers to cross-check historic droughts and cold spells with recorded eclipses and tidal data. Chinese scholars combined their own ancient eclipse records with modern science, offering long timelines to study. Even today, scientists continue to ask how lunar cycles may have influenced agriculture and weather patterns in history. These studies remind us that the Moon has not only shaped the tides, but may have quietly shaped the course of civilizations through its subtle effect on climate. Discovery 45. Advances in lunar cartography. The 19th century was a golden age of lunar mapping. With telescopes improving and photography emerging, astronomers were able to produce the first truly detailed maps of the Moon. Johann Heinrich Mädler and Wilhelm Beer's Lunar Atlas of 1837 became a milestone, cataloging craters, mountains, and plains with accuracy never seen before. For the first time, the Moon was no longer just a glowing disk in the night sky. It was a world with geography, a place that could be studied and documented systematically. These maps inspired scientists and the public alike. They fueled a surge of interest in lunar exploration and even influenced the imagination of writers and artists. The Moon became less mysterious, but no less fascinating. Today, the legacy of those early maps lives on in digital lunar cartography. China's Chang'e missions have expanded on this vision, creating fully 3D maps with laser altimetry and high-resolution imaging. What began as hand-drawn sketches has evolved into digital terrains accurate down to the meter. Discovery 46. Lunar dust speculation. During the 1800s, astronomers puzzled over a faint glow they sometimes observed on the Moon. Some proposed that a fine, powdery dust covered its surface, scattering sunlight in unusual ways. At the time, this idea was speculation, but it sparked both scientific and popular interest. Writers imagined explorers sinking into endless seas of dust, while scientists debated whether such material could exist. Centuries later, lunar landings confirmed that the surface is indeed covered by regolith, a layer of sharp, glassy dust created by countless meteorite impacts. Far from soft and harmless, this dust clings to spacesuits, damages equipment, and poses a hazard to astronauts. Modern rovers like China's U-2 and U-22 study it carefully, since mastering its properties is crucial for future lunar bases. What began as a curious 19th century theory has become one of the biggest challenges for sustainable human presence on the Moon. Discovery 47. The moon and volcanic theories. Throughout the 19th century, one of the most heated debates in lunar science was the origin of the moon's craters. Many astronomers argued they must be volcanic, resembling the calderas and lava basins of Earth. The circular shapes and central peaks seemed to match volcanic formations. This volcanic theory dominated scientific thought for decades, painting the moon as a geologically active world. It wasn't until the 20th century that impact cratering was widely accepted as the main explanation. Yet those early volcanic theories were crucial. They introduced the idea that the moon had a dynamic history, sparking the first serious geological interpretations of its surface. Chinese space missions have added a modern perspective, confirming that while most craters are impact-formed, volcanic activity did play a role in shaping regions like the Maria. Thus, the old debate was not entirely misplaced. The 19th century fascination with lunar volcanoes anticipated discoveries that would still be unfolding 2 centuries later. Discovery 48. Double star occultation measurements. The moon's passage across the sky became an invaluable measuring tool in the 19th century. When it passed in front of stars, an event known as an occultation, astronomers timed the disappearance and reappearance with great accuracy. These timings revealed not only details about the moon's size and motion, but also helped refine star catalogs. Double star occultations, in particular, provided opportunities to measure distances and angular separations at levels of precision otherwise impossible at the time. This turned the moon into a kind of natural instrument, an astronomical ruler against the backdrop of the cosmos. These methods improved celestial navigation and deepened our knowledge of both the moon and the wider universe. Modern astronomers, including Chinese researchers, still use occultations for calibration and astronomical studies, proving how a centuries-old technique remains relevant in the digital age. Discovery 49. Lunar lava tubes. Potential future habitats. Beneath the moon's surface lie hidden structures that could change the way humanity explores space. Lunar lava tubes. These vast underground tunnels were carved billions of years ago by flowing lava during periods of intense volcanic activity. Once the lava drained away, it left behind hollow passages that may stretch for tens of kilometers. Orbiters, including Japan's Selene, Kaguya mission, and China's Chang'e orbiters, detected collapsed skylights, openings in the lunar crust that may lead to intact lava tubes below. Some of these caverns are so large they could fit entire cities inside. Why does this matter? The moon's surface is bombarded by radiation, extreme temperature swings, and micrometeorites. But inside a lava tube, explorers would be shielded naturally, without needing massive protective structures. These caverns could become humanity's first lunar bases, offering stable environments for living, research, and even agriculture. The discovery of lunar lava tubes transformed them from geological curiosities into potential gateways for colonization. Far from being empty voids, they may one day serve as humanity's safe havens on the moon, protecting our first steps toward becoming a multi-planetary species. Discovery 50. The moon as a celestial laboratory. By the close of the 19th century, scientists began to think of the moon as more than a subject of observation. They imagined it as a kind of celestial laboratory, a natural stage for testing the laws of physics and geology. Without an atmosphere or weather, its surface preserved craters and landscapes for millions of years, offering a clear record of cosmic history. The moon became seen as a place where fundamental questions about cratering, volcanism, and orbital mechanics could be studied directly. This vision also made the moon central to dreams of future exploration. If humanity ever ventured beyond Earth, the moon could serve as a training ground or stepping stone to Mars and beyond. Today, this philosophy drives modern programs, especially China's space ambitions. Their Chang'e missions treat the moon not only as an object of study, but as a proving ground for deeper space travel. The 19th century's vision of the moon as a laboratory is now closer than ever to becoming reality. Discovery 51. The moon's gravitational influence on Earth's rotation. In the 19th century, astronomers realized that the moon's gravitational pull did far more than create tides. It was slowly altering the very rhythm of Earth itself. Careful astronomical records, especially of eclipses preserved over centuries, revealed that Earth's rotation was gradually slowing down. Days were imperceptibly lengthening as tidal friction between Earth's oceans and the moon drained rotational energy. This process, known as tidal braking, also meant the moon was slowly drifting farther away from Earth, a fact now confirmed by modern laser ranging. At the time, this was a revolutionary concept. The moon was not only influencing the oceans, but subtly changing the passage of time on Earth. Ancient Chinese records of eclipses helped validate this, providing centuries-long data sets that matched Western calculations. Today, with lunar laser reflectors placed on the surface, including those measured by Chinese observatories, we know the moon retreats at about 3.8 centimeters per year. The discovery highlighted the deep, dynamic relationship between Earth and its companion, showing that even time itself is shaped by the moon. Discovery 52. The moon's possible role in stabilizing Earth's axis. By the late 19th century, scientists began to ask a profound question. Why is Earth's climate relatively stable compared to that of other planets like Mars? One proposed answer was the moon. With its significant mass and gravitational influence, the moon helps stabilize Earth's axial tilt, preventing it from wildly shifting over millions of years. Without the moon, Earth might experience chaotic changes in tilt, leading to extreme climate fluctuations, making life as we know it far more difficult to sustain. This insight reframed the moon as more than a satellite. It was an anchor of habitability. By keeping Earth's tilt steady at around 23.5 degrees, the moon ensured seasonal cycles were relatively predictable and survivable. Modern simulations confirm this stabilizing effect, and Chinese researchers continue to explore how this balance influenced Earth's evolutionary history. In this sense, the moon is not just a neighbor in the sky, but a guardian of Earth's long-term stability, helping make our planet a cradle of life. Discovery 53. The moon's role in calendar systems. For millennia, humanity has looked to the moon as a natural timekeeper, but in the 19th century, astronomers began to study its role in calendars with scientific precision. Cultures worldwide had used lunar months for farming, festivals, and religious events. But now efforts were made to standardize lunar calendars by integrating them with solar years. The Chinese lunisolar calendar, deeply tied to traditions like the Mid-Autumn Festival, underwent refinements using Western astronomical methods, blending ancient heritage with modern accuracy. The recognition of the moon as a global timekeeper underscored its universality. Whether in China, Europe, or the Middle East, societies shared a reliance on its cycles to structure life. The moon's phases became a bridge between cultures and a reminder of the rhythms uniting humanity. Today, the moon continues this symbolic role, with Chinese lunar missions named after Chang'e, connecting modern space exploration to a timekeeping tradition thousands of years old. The moon's role in calendars reminds us that science and culture often meet under its glow. Discovery 54. Advances in lunar topography. During the 19th century, advances in telescopes and shadow measurement techniques allowed astronomers to chart the heights of lunar mountains and the depths of its craters with surprising accuracy. By studying the length of shadows cast during different lunar phases, they estimated that some lunar mountains rivaled or exceeded Earth's tallest peaks, while craters stretched for hundreds of kilometers. This realization shattered the image of the moon as a flat, featureless orb and revealed it to be a rugged and alien world. These efforts marked the birth of three-dimensional lunar mapping. For the first time, maps began to capture not just positions of features, but also their relative elevations, giving scientists a better sense of the moon's true landscape. Today, China's orbiters use laser altimetry to produce stunningly detailed 3D maps that would have astonished 19th century observers. The shift from flat sketches to dynamic topography was more than a technical breakthrough. It reshaped humanity's imagination, allowing us to see the moon as a real place, full of mountains, valleys, and vistas waiting to be explored. Discovery 55. The Moon and the Birth of Selenography. The 19th century gave rise to a new scientific discipline, selenography, the detailed study of the moon's surface features. With improved telescopes and systematic mapping, astronomers began cataloging craters, plains, rilles, and mountains with a rigor once reserved for geography on Earth. Observers across Europe compared drawings, standardized names, and refined measurements, creating a shared body of knowledge that made lunar studies a legitimate scientific field. In China, where lunar observation had long been tied to culture and tradition, selenography merged with ancient practices. The combination of Western science and Eastern heritage helped frame the moon as both a cultural symbol and a scientific world. Today, selenography lives on in digital form, with orbiters like China's Chang'e missions generating precise lunar atlases. The legacy of the 19th century was clear. The moon had transitioned from a poetic mystery to a world whose features could be systematically studied and classified. Discovery 56. The moon's librations studied in detail. One of the more subtle discoveries of the 19th century was the detailed study of lunar libration, the moon's slight wobbling as it orbits Earth. This effect allows us to see about 59% of the lunar surface over time, rather than just one face. By carefully observing these wobbles, astronomers revealed glimpses of the moon's hidden edges, features that were sometimes visible and sometimes concealed. This discovery not only expanded humanity's access to the moon's surface, but also deepened understanding of orbital mechanics. The recognition of libration showed that the moon was not entirely static from our viewpoint. It was dynamic, shifting just enough to tease us with sights beyond its average face. Today, Chinese orbiters and telescopes continue to take advantage of librations, capturing high-quality data from regions once seen only fleetingly. The 19th century study of libration demonstrated that even small motions could open big windows into new worlds. Discovery 57. The Moon and Long Baseline Astronomy. In the 19th century, astronomers turned the moon into a tool for exploring the universe itself. By timing lunar occultations from widely separated observatories, they could measure parallax angles with improved accuracy. This technique refined star catalogs, determined stellar distances, and even improved calculations of Earth's size and position in space. The moon thus became a bridge between Earth and the stars, a kind of reference point anchoring astronomy. These long baseline experiments demonstrated how the moon was not just a subject of study, but also an essential tool for cosmic measurement. Today, China uses lunar occultation data in radio astronomy, combining modern technology with the very same principles developed centuries ago. The moon's role as a ruler of the heavens continues, reminding us that exploration is often about using one discovery to unlock another. Discovery 58. The Moon and Seismology Theories. Even before seismology was fully developed on Earth, 19th century scientists speculated about moonquakes. Some believed that shifting terrain or tidal stresses from Earth's gravity might cause tremors on the moon. Others suggested cooling and contraction of the lunar crust could create seismic events. Although these ideas were unproven, they sparked important debates about whether the moon was geologically dead or still active. These early discussions laid the foundation for later lunar seismology, which became a reality during the Apollo missions. Instruments placed on the moon confirmed that moonquakes do exist, though they are weaker and caused by tidal stresses, meteorite impacts, or thermal expansion. Today, Chinese missions are investigating seismic activity on the lunar far side, pushing this field forward. The 19th century speculation, while premature, showed how curiosity often outpaces technology. Ideas sometimes arrive long before the tools to test them. Discovery 59. The Moon and Cultural Astronomy in China. Despite political upheavals in 19th century China, the moon retained its central place in culture and science. Scholars recorded eclipses, tracked lunar phases, and preserved traditions tied to festivals and agriculture. Western telescopes introduced during this era blended with China's ancient observational methods, creating a unique fusion of tradition and modernity. Eclipse records in particular proved invaluable, linking ancient data with modern astronomical calculations and confirming the accuracy of centuries-old observations. The moon thus became not only a scientific object, but also a cultural bridge between China's past and its emerging future. Today, The naming of Chinese lunar missions after Chang'e reflects this legacy, blending myth, culture, and cutting-edge exploration. The 19th century was a moment when cultural astronomy helped preserve continuity, proving that science and tradition could thrive together under the same moon. Discovery 60. The moon's influence on biological rhythms. In the 19th century, naturalists began to systematically study how the moon influenced living organisms. They discovered that many animals and plants aligned their life cycles with lunar rhythms. Corals, for example, spawned in mass synchrony with full moons, while nocturnal animals adjusted activity depending on moonlight levels. Farmers, too, had long relied on lunar phases to guide planting and harvesting, and these practices gained scientific validation. This expanded the moon's significance beyond physics and geology into biology. It revealed that the rhythms of life on Earth are deeply tied to our celestial neighbor. In China, where agricultural traditions already followed lunar calendars, this connection between biology and the moon reaffirmed centuries of practice. Today, biologists continue to investigate how lunar cycles influence circadian rhythms and ecosystems. The recognition in the 19th century that the moon shaped life itself marked one of the most profound expansions of lunar science. Discovery 61. The moon's gravitational anomalies. In the 1960s, when spacecraft began orbiting the moon, scientists noticed their paths were unexpectedly altered, as if invisible hands were tugging at them. These turned out to be gravitational anomalies, or mascons, mass concentrations, buried beneath the lunar crust. Found mainly under giant impact basins like Mare Imbrium, Oceanus Procellarum, and Mare Orientale, mascons are areas of higher-than-expected gravity caused by dense material, possibly from ancient lava flows or the rebound of the crust after massive asteroid impacts. This discovery forced engineers to rethink lunar navigation. Without correcting for mascons, orbiters would drift, crash, or consume excess fuel. NASA, Soviet, and later Chinese missions had to carefully map and compensate for these hidden gravitational traps. China's Chang'e orbiters contributed high-resolution gravity maps, revealing the fine structure of mascons in unprecedented detail. Today, these anomalies are more than navigation hazards. They are windows into the moon's violent history and its deep interior. Mascons showed us that beneath the calm gray surface lies a hidden geological record of impacts and volcanism. Discovery 62. The solar wind and lunar soil. When Apollo astronauts returned lunar samples, scientists discovered something remarkable. The soil was laced with particles from the solar wind. Unlike Earth, the moon has no atmosphere or global magnetic field to shield it. So for billions of years, its surface has been directly bombarded by charged particles from the sun. Lunar regolith acts like a cosmic sponge, trapping helium, hydrogen, neon, and even rare isotopes like helium-3. This turned the moon into a natural archive of solar history, preserving information about how the sun has evolved over eons. By analyzing these particles, scientists can reconstruct the changing intensity of solar radiation across time. Chinese researchers, especially in the Chang'e 5 mission, studied helium-3 levels with new precision, not just for science, but also for future technology, since helium-3 is a potential clean fuel for nuclear fusion. What once seemed like barren gray dust was revealed as a rich scientific library, recording both solar activity and clues for humanity's energy future. Discovery 63. The Moon as a witness to Earth's early history. Earth's surface is constantly erased by tectonics, erosion, and volcanism, but the Moon's surface remains frozen in time. In the 1970s, scientists realized the Moon preserves a pristine record of the early solar system, especially the violent era called the Late Heavy Bombardment, around 4 billion years ago, when asteroids hammered both Earth and the Moon. On Earth, nearly all traces of this period were destroyed, but the Moon still bears the scars. This makes the Moon a unique time capsule of Earth's infancy. By studying its craters and rocks, we can piece together the chaotic environment in which Earth evolved and life first arose. Chang'e 5 samples recently revealed evidence of long-lasting volcanic activity and impacts, deepening our knowledge of this era. Without the Moon, our understanding of Earth's earliest environment would be incomplete. In many ways, the Moon is not just Earth's companion, it is its memory. Discovery 64. Water on the Moon, first clues. For most of the 20th century, scientists believed the Moon was bone dry. Apollo samples seemed to confirm this, showing no water molecules at all. But by the 1990s, spacecraft instruments began detecting faint hydrogen signals in lunar soil, particularly near the poles. These tantalizing hints suggested water ice might survive in permanently shadowed craters where sunlight never reaches. The idea was revolutionary. The Moon, once thought sterile, might harbor frozen reserves of water. China's Chang'e orbiters confirmed hydroxyl molecules and water-related signatures across the surface, and later missions even mapped potential ice deposits. These discoveries transformed exploration strategies. Water on the Moon is not just a scientific curiosity, it is a resource. It can support astronauts, grow food, and even be split into hydrogen and oxygen for rocket fuel. What started as a faint signal became one of the most important revelations in lunar science. Discovery 65. Volcanic glass beads and hidden water. A re-examination of Apollo samples in the early 2000s revealed something astonishing. Microscopic volcanic glass beads, created during ancient eruptions, contained traces of water. This was the first evidence that the Moon's interior wasn't completely dry. These tiny beads suggested that deep within the lunar mantle, small amounts of water were locked away, preserved for billions of years. China's Chang'e 5 mission later recovered similar beads, confirming that the Moon's interior had once held more volatile materials than scientists believed. This discovery reshaped theories of the Moon's formation, showing that it retained part of its volatile inventory, despite the violent heat of its birth. These glass beads are more than geological relics. They are silent witnesses of the Moon's fiery past and reservoirs of potential future resources. Discovery 66. Permanently shadowed craters as cold traps. At the Moon's north and south poles, some craters are so deep and steep-walled that sunlight has never touched them, not for billions of years. These regions are called permanently shadowed craters or cold traps, and they are among the coldest places in the solar system. with temperatures plunging below 200 degrees Celsius. In the 1990s, data from NASA's Clementine and Lunar Prospector missions hinted that hydrogen, possibly water ice, was hiding there. Later, India's Chandrayaan-1, NASA's L-Cross impactor, and China's Chang'e orbiters confirmed that these regions really do contain ice. This was a paradigm shift. Scientists once thought the moon was bone dry, but these dark craters are like natural freezers, preserving water molecules delivered by comets, asteroids, and solar wind over billions of years. For science, this discovery revealed how water moves around airless worlds and how planetary bodies store volatiles. For exploration, it was a goldmine. Ice in these craters could provide drinking water, oxygen to breathe, and hydrogen fuel for rockets. China has placed great emphasis on the lunar South Pole in its upcoming Chang'e 7 and Chang'e 8 missions, aiming to study and even use this frozen treasure. What once looked like endless darkness has now become the most valuable real estate on the moon. Discovery 67. Helium-3, the fuel of the future. While water ice is critical for survival, another hidden treasure on the moon could power civilizations: helium-3. This rare isotope is carried to the lunar surface by the solar wind and has accumulated in the regolith over billions of years. Unlike Earth, which is shielded by a magnetic field, the moon has absorbed vast quantities of this material. Helium-3 is so important because it is a potential fuel for nuclear fusion, the same process that powers the sun. Unlike current nuclear power, helium-3 fusion would produce little to no radioactive waste, offering a nearly limitless supply of clean energy. Theoretically, just a few tons of helium-3 could power an entire country for a year. In the 1980s, researchers first proposed that the moon might serve as a helium-3 mine. Since then, China has shown a strong interest in this idea, and its Chang'e 5 samples are being tested for helium-3 content. If future technology can unlock its use, the moon could become humanity's ultimate energy bank. This discovery reframed the moon from being just a scientific object into a strategic energy reserve, one that may determine the future of space economies. Discovery 68. Lunar dust and its unique behavior. When Apollo astronauts stepped onto the moon, they encountered an unexpected and dangerous problem: lunar dust. This isn't dust like we know on Earth. It is made of sharp, glass-like particles created by billions of years of micrometeorite impacts. Without wind or water to smooth them, the grains remain jagged and cling to everything due to electrostatic charge. The dust wore through spacesuits, clogged joints, scratched visors, and even irritated astronauts' lungs. Neil Armstrong described it as smelling like burnt gunpowder. Later missions confirmed how destructive it could be. Chinese missions also studied dust behavior in detail. The U-2 rovers observed how dust moves under sunlight and mechanical activity, revealing that it can even levitate above the surface due to static electricity. Understanding this is critical. Future lunar habitats, machines, and solar panels must be designed to withstand the relentless assault of dust. But dust is also a record keeper. Each grain contains traces of solar wind particles, cosmic rays, and ancient impacts. It is both a hazard and a history book. The discovery of dust's strange properties turned it from a nuisance into one of the most important subjects of lunar science. Discovery 69. Moonquakes and a seismically active moon. Most people imagine the moon as completely dead and silent, but in 1969, Apollo seismometers revealed a shocking truth. The moon shakes. These moonquakes come in 4 types. Deep quakes caused by tidal forces from Earth. Shallow quakes possibly linked to tectonics. Thermal quakes triggered by extreme temperature changes, and those caused by meteorite impacts. Some shallow moonquakes were powerful, up to magnitude 5 on the Richter scale, and lasted much longer than earthquakes, sometimes for 10 minutes straight due to the moon's rigid, dry crust. This suggested the moon still has an active interior, cracking and shifting as it slowly cools and contracts. China's future Chang'e 7 and Chang'e 8 missions plan to deploy advanced seismometers, especially on the far side, to map these deep tremors more precisely. The discovery of moonquakes shattered the old image of a frozen, lifeless rock. Instead, the moon is still alive with subtle activity, its surface slowly reshaped from within. Discovery 70. Evidence of lunar tectonics. Alongside moonquakes, orbiters discovered another clue to lunar activity: vast fault scarps, or cliff-like features formed when the moon's crust breaks and shifts. High-resolution imaging from NASA's Lunar Reconnaissance Orbiter and Chinese Chang'e orbiters revealed thousands of these scarps scattered across the surface. What shocked scientists was their age. Many of them are geologically young, less than 50 million years old. That may sound ancient, but on the scale of the solar system, it means they formed very recently and may still be forming today. The moon is literally shrinking as it cools, and its surface is crumpling like the skin of a drying fruit. This was revolutionary. The moon wasn't just a relic of the past. It was still evolving, even if slowly. Chinese missions continue to monitor these scarps for fresh signs of activity. If astronauts return to the moon, they may one day witness its surface shift beneath their feet. Discovery 71. The mystery of lunar swirls. Perhaps the most visually stunning mystery of the moon is its lunar swirls, ghostly looping patterns of bright and dark soil that stretch across the surface like painted brushstrokes. The most famous, Reiner Gamma, can be seen even from Earth. What makes them strange is that they don't match craters or topography. Instead, they are linked to local magnetic fields. These fields seem to shield the soil from solar wind, preserving its brightness while surrounding areas darken. Chinese orbiters contributed magnetic data that helped refine these theories, but the origin of swirls is still not fully understood. Were they created by comet impacts, volcanic vents, or ancient crustal magnetism? Nobody knows for sure. The swirls remain one of the moon's great puzzles, enigmatic, beautiful, and a reminder that even in a world we think we know, deep mysteries remain written on its surface. Discovery 72. The moon's role in understanding Earth's history. The moon is more than just a companion in the night sky. It is a geological time machine. Unlike Earth, which is constantly reshaped by plate tectonics, erosion, and weather, the moon has remained largely unchanged for billions of years. Its surface has preserved scars from ancient asteroid impacts and volcanic eruptions that were erased long ago from Earth's surface. By studying these craters and lunar rocks, scientists gained a deeper understanding of Earth's violent early history. The Moon revealed that our planet endured a period of heavy bombardment 3.8 to 4.1 billion years ago, when massive impacts reshaped both worlds. Without the Moon as a preserved record, much of this knowledge would have been lost forever. China's Chang'e 5 mission, which returned fresh samples in 2020, added crucial new data to refine this timeline. These findings suggest that the same impacts which left marks on the Moon also influenced Earth's evolution, possibly even delivering key ingredients for life. Thus, the Moon is not only a celestial neighbor, but a silent witness to the hidden past of our own planet. Discovery 73. The Moon and the origin of water on Earth. Water is the essence of life, yet its origins on Earth remain one of science's greatest mysteries. The Moon, surprisingly, has become a crucial piece of this puzzle. For decades, scientists believed the Moon was bone dry. However, discoveries of water molecules trapped in lunar soil, as well as frozen water in permanently shadowed craters at the poles, challenged this assumption. These findings also opened a window into Earth's own watery history. Many scientists now believe that comets and asteroids bombarded both Earth and the Moon billions of years ago, delivering water and organic molecules. The lunar surface, lacking atmosphere and tectonic activity, preserved this record in a way Earth could not. By comparing isotopes of hydrogen in lunar water with those found on Earth, scientists are piecing together the story of how our oceans formed. China's Chang'e 5 mission contributed by analyzing volcanic glass beads that may have once stored water deep inside the Moon's mantle. These results suggest that both external impacts and internal geological processes contributed to lunar water. By extension, the Moon is teaching us how Earth became a blue, life-bearing world in a universe that seems otherwise dry. Discovery 74. Seismometers revealing the Moon's active interior. For many years, the Moon was considered a dead world, geologically inactive for billions of years. That perception began to change when Apollo astronauts left behind seismometers in the 1970s, detecting so-called moonquakes. Decades later, China's Chang'e 3 lander revived this research by deploying its own seismic instruments, confirming that the Moon is not as silent as once believed. These instruments detected 4 main types of moonquakes: deep quakes caused by tidal stresses from Earth's gravity, shallow quakes linked to tectonic movement, thermal quakes caused by the heating and cooling of the lunar crust, and impact quakes from meteor strikes. The discovery was groundbreaking because it revealed that the Moon's crust and mantle are still shifting, and that its interior may retain more heat than scientists assumed. Some shallow moonquakes were powerful enough to potentially damage future lunar bases, making this research critical for human settlement. Seismology also revealed density variations inside the Moon, providing evidence for a small liquid core. The Moon, it turns out, is not a frozen relic. It is still alive with subtle geological activity, waiting to be fully understood. Discovery 75. Evidence of young volcanism, surprising late activity. For decades, The prevailing belief was that the moon's volcanic activity ended over 1 billion years ago. Its surface, scarred by ancient lava plains known as Maria, seemed to tell the story of a world that cooled and died early in its history. But in 2020, China's Chang'e 5 mission shattered this assumption. The samples it brought back contained volcanic rocks only 2 billion years old, making them 1 billion years younger than any previously collected lunar samples. This discovery revealed that the moon's mantle retained enough heat to sustain volcanism far longer than expected. The implications were profound. If volcanism persisted so late, then the moon's interior may have contained more radioactive elements, which produced heat through decay than scientists had assumed. This changed our understanding of lunar thermal evolution and forced a re-evaluation of planetary cooling models across the solar system. The discovery also raised questions about what other secrets might lie hidden beneath the moon's surface. The moon, once thought to be geologically simple, turned out to have a far more complex and dynamic history than anyone imagined. Discovery 76, the moon's far side. A hidden world revealed for millennia, humanity saw only one face of the moon. The far side remained hidden until 1959, when the Soviet Luna 3 spacecraft captured the first grainy images. What it revealed was startling. The far side looked nothing like the near side. Instead of vast volcanic plains, it was dominated by rugged highlands and deep craters. Yet no nation had ever landed there until China's Chang'e 4 mission in 2019. It became the first spacecraft in history to land softly on the far side, opening an entirely new chapter of exploration. Chang'e 4 and its Yutu-2 rover discovered rocks with unique compositions, confirming that the far side's crust is thicker than the near side's. Scientists also studied the massive South Pole Aitken Basin, one of the largest impact structures in the solar system, which may expose materials from the moon's mantle. These discoveries explained why the two lunar hemispheres evolved so differently and provided clues about the early dynamics of the Moon-Earth system. The far side, once hidden and mysterious, is now becoming a key to understanding the moon's deepest secrets. Discovery 77. The moon as a record of solar activity. The sun is the driving force of life on Earth, but its activity has not always been stable. Understanding its history is crucial to knowing how it influenced Earth's climate and evolution. The moon, surprisingly, holds part of this record. Its surface soil, or regolith, contains tiny particles implanted by the solar wind, charged atoms of hydrogen, helium, and other elements ejected by the sun. Unlike Earth, which has a magnetic field and atmosphere that shield it, the moon is directly exposed, making its surface a natural collector of solar history. By studying these isotopes trapped in lunar soil, scientists reconstructed patterns of solar activity over billions of years. This discovery revealed how solar winds changed over time, providing data that Earth's atmosphere erased. China's Chang'e missions added to this record by collecting new samples for analysis, confirming variations in solar wind composition. This insight is vital not only for understanding Earth's past climate, but also for predicting future solar storms that could disrupt satellites and power grids. The moon, in this sense, serves as the sun's archive, silently recording its moods and changes across cosmic time. Discovery 78, a new lunar mineral, changesite, Y. The Chang'e 5 mission returned to Earth with over 1.7 kilograms of lunar soil, and within these precious samples lay a groundbreaking find, a brand new lunar mineral named changesite, Y. This phosphate mineral, transparent and columnar in shape, was identified after painstakingly examining over 140,000 tiny lunar particles. What made this discovery historic was not just its rarity. China became the third nation after the US and Russia to discover a new lunar mineral, but also its potential significance for humanity's future. Embedded within the mineral is helium-3, an isotope seen as a potential game-changer for clean nuclear fusion energy. If harnessed, helium-3 could provide a nearly limitless energy source without the radioactive waste produced by current nuclear power. While practical fusion technology is still in development, the confirmation of helium-3 in a newly discovered mineral reinforces the Moon's role not just as a site of scientific curiosity, but as a strategic resource base for future generations. Discovery 79. The Moon's extended volcanic youth. The long-standing assumption that the Moon became geologically dead around 3 billion years ago was shattered by the analysis of basalt rocks collected by Chang'e 5 from the Oceanus Procellarum region. Radiometric dating revealed these samples to be only 2 billion years old, showing that lunar volcanism persisted almost 1 billion years longer than previously believed. This raised profound questions about how the Moon maintained enough internal heat to produce volcanic activity for so long. The findings suggest that the Moon's mantle may have contained concentrated pockets of radioactive elements, generating heat over extended periods. This forces scientists to reconsider models of the Moon's thermal history, shifting the picture from a world that quickly cooled into a geologically frozen body to one that remained dynamically active much longer. By extending the Moon's volcanic timeline, Chang'e 5 redefined how we understand not only lunar history, but also planetary evolution in general. Discovery 80. Peering into the far side's mantle. The Chang'e 4 mission, humanity's first landing on the far side of the Moon, gave scientists an unprecedented opportunity to peer into the Moon's deep geological structure. Touching down in the South Pole Aitken Basin, the largest impact crater in the solar system, the mission deployed its U-22 rover to survey the terrain and probe beneath the surface. Using its lunar penetrating radar, U-22 revealed subsurface layers extending to 40 meters deep, shaped by ancient lava flows and the violent history of asteroid impacts. More importantly, spectrometer readings detected minerals such as olivine and low-calcium pyroxene, materials believed to originate from the Moon's mantle rather than its crust. This provided the first tangible evidence of mantle material on the surface, something scientists had long hypothesized but never directly observed. By accessing this hidden layer, Chang'e 4 not only confirmed theories about the Moon's inner structure, but also opened the door to studying how rocky worlds, including Earth, evolved from their interiors outward. From early sketches of craters to the analysis of returned lunar samples, each discovery has transformed the Moon from a celestial mystery into a tangible world. As modern missions build upon this centuries-long legacy, the Moon now stands not only as a record of our solar system's past, but as a crucial proving ground for humanity's future among the stars.